I'm also a DoD acquisition professional with a good background in test and evaluation, systems engineering, and program management. So I'm trying to take some of the rigor and the discipline of the DoD acquisition system and bring them to the NOAA UAS program. So you'll see a lot of standard systems engineering practices, rigor, especially when it comes to studying the problem up front. So before you go out there in the field and get dirty in the mud and you know, buy expensive platforms and sensors, study the problem. Figure out what you really want. What's the data need, the end data need. And maybe we could, you know, maybe it's a satellite data source we can get for free or near free or a manned aircraft. But before you go in the field, really study the problem. We're going to talk a little bit about that. So this is a concept that I've been using now for the last 6 years. I come up here every time I say, hey, we love Alaska because it's our aircraft carrier in the Arctic. And Harry doesn't embrace it because he's an Air Force aviator, so it hasn't stuck up. But as a maritime aviator, you realize how important the aircraft carrier is because you show up to the problem, right? When you take off from the aircraft carrier, you're already on station. There's no transit time. You're there, you get feet dry, and you're doing your business. Or if you're looking for a submarine, it's sometimes right below you. So it's a great way to cut out transit time, to get to work. And we know how tough it is to get up here in Alaska. But the really hardy people of Alaska are right here in the room, and they bring the hardy platforms to the problem. And you guys really know how to do business here, right? I don't call somebody in Key West to do an Arctic mission. It's just not going to work out. But you folks know how to handle these mission sets. So here's a couple things I'm going to talk about. There's a Puma launching from the Healy, from the icebreaker. We did that last year. And we've been flying the Global Hawk. We did a number of storms this year, including weather observations that affected you all in February. So Justine did a nice job teeing up the overarching strategy of NOAA. We drilled down a little bit at the NOAA UAS program. And again, these are the things that we've been focused on. High impact weather, marine monitoring, and polar monitoring. And all those things converge right here in Alaska. You make it real easy on us. So yesterday we had a great briefing from Robin on looking for marine mammals. During that very same mission, we were doing atmospheric sampling. So that says the P3 guy, I'm always thinking, hey, we gotta do multi-mission. You're never doing just one thing out there. And if you put an atmospheric sensor on your UAS, an inexpensive atmospheric sensor on your UAS, you're always doing a NOAA mission. So think about that. And we've been working on that strategy, and I'll tell you a little bit more about that. So one of the great things about the Global Hawk work we've been able to do is go to those remote sites. So you see all the tracks up on the upper left there. And these are the missions we flew this summer over 4 different hurricanes. And look how we take off out of Virginia and we're flying off the coast of Africa. We're the only aircraft that goes out that far and does that. Some of the P3s, the G4, and the C-130s will pick up the storm around here, but we're actually going pretty far out front to see the genesis of the hurricane. So trying to get the data that will help our forecasters give us a better forecast and protect our country from this invading weather. We talked a little about shipboard operations. Here's the Scan Eagle flying last summer from the beach of Liptok Point. It joined up with us when we were flying the Puma off of the icebreaker Healy, and we did a great manned-unmanned teaming piece out there. And I have a video to show a Puma flying over 2 manned helicopters that we were doing during the search and rescue component of that exercise. Really eye-watering. One of the things we've been working on over the last few years is a maritime strategy when it comes to unmanned systems. So when you're flying, each aircraft carrier doesn't get a chance to pick its own aircraft. You know, so the fighter for the Navy is the F-18, and the good thing about that is you have, when the plane takes off from one carrier, you go to another carrier, get gas, get parts, and you have standardization operations, you can swap pilots, you can swap parts. And you need to kind of go to that approach when you're doing shipboard operations here. One of the success stories we've seen with our maritime partners is with Puma. Now, every one of the maritime services is own and operate Pumas. So the Navy, the Coast Guard, NOAA, and now the Danes and the Dutch have also bought into them. So they're flying off their vessels. And a lot of the work we've done has spiraled into how the other services can use them. We talk a little bit about our research and development. I mean, you go over the 4 Ds all the time. The dull, dirty, dangerous, and denied. You guys are in a denied area up here. It's just hard to do operations in Alaska or North Alaska. Unmanned systems could help. But now we're starting to get more into the why. I'm doing a bunch of analysis now on say, the Global Hawk work we're doing. So the hurricane hunting aircraft, the P-3 and C-130s, burn about 750 gallons per hour, right? The Global Hawk burns about 75 gallons per hour. And you'll see that the Global Hawk, it goes on station, and it'll do a 24-hour station, on-station time in one flight. During that time, we watch the P-3s and the C-130s come and go. They spend more than 50% of their time in transit. And for them to get 24 hours on station often takes them 4 or 5 different evolutions. So think about that. Not just the cost in gas, but also the carbon footprint. So these are things we're starting to examine more and more. And we're putting together that larger story. So you see on the bottom there, this is a picture of a Puma on board one of our destroyers, USS Spout. It's currently deployed in the Atlantic. They're using the Puma net capture system, which we did most of the research and development on, testing on our small research vessels. So a good success story, maritime services coming together to bring new technologies out to the fleet. We talked a little about a strategic view. And this goes for, if you're trying to capture funding, go back to the national strategy, because that's the components that get funded. And we do that as one of the services. So you start off with the national strategy for the Arctic, and that was published in 2013. Ours followed with the Arctic Vision and Strategy. And what we did is we're going through each of those components and trying to put mission sets on, see which missions we can capture using unmanned systems. So we did a formal analysis of all terms based on DoD practices. And luckily, a lot of our stuff breaks out because we want high TRL, program of records. You know, we want DoDs or other partners to spend all those non-reoccurring engineering dollars. And then we'll take advantage of the platforms once they go in production. And then maybe put on different sensors and do things like that to fulfill our applications. But that's been very, very successful for us. And as Jay said, I mean, getting military surplus or military partnered platforms, NASA partnered platforms, that's how a lot of the NASA platforms, the Global Hawks, all came from the Air Force. So it's worked for the other government partners. And then again, this is the area we're trying to cover. These are the mission sets, and these are the missions we've flown. And I'm not going to go into each one of them, but the slideshow will be available. If you need any data or any specifics, please talk to me or Justine or Phil. We can give you drill down a couple levels. But the speakers behind me all supported this effort. So you're going to hear from our academic partners, both in Mississippi State and University of Alaska. You can hear from the National Weather Service. You're going to hear from Precision, who we have a crater with, who's doing really advanced shipboard operations in the Arctic and out in the middle of the oceans. So these are all things that we've been putting together, very, very successful. And one thing that we've been exploring is the rapid response component of using UASs. So sometimes it's impossible, especially post-disaster, to get a manned aircraft in the air. Sometimes it can be very effective to get a small UAS just to get those aerial images, and we'll talk a little bit about that. So we teed this up a little bit earlier. This year, in 2016, we flew about a total of 310 flight hours with the Global Hawk. And most people right now are interested in this and all the flights we had over the hurricane, including Matthew. But I'm going to back up to the missions that we flew for the El Nino rapid response in the Pacific and Arctic weather. So we flew a total of 3 science missions with 25.8 flight hours. So about 25 hours per mission. We took off and we were immediately on station. We were flying out of NASA Armstrong. We dropped 90 SONs during the month of February, so about 30 SON flight hours. And we were able to capture the atmospheric rivers, the weather storms, the winter weather storms that were coming across the Pacific, and ended up dumping a bunch of water, high winds, flooding, coastal erosion on y'all at the end of February. in the beginning of March. And just quick, we're doing data impact studies right now. All the cool colors, so the blues, the purples, that shows positive influence on the models. So we were pretty successful in helping out Alaska here, especially in the 72-hour forecast. So good stuff, flying, extended ranges, long endurance with multiple sensors, but highlighting really doing the signs. Okay, this year the goal was, Robin talked a little bit about the cost of operations. I track one of the key components if you're an aviation guy. The expense typically comes from things that spin, so the engines, and also the landing cycles, time in transit. So if you're minimizing that, things are good. Global Hawk, you're looking at a single engine jet, that's a good thing. 75 gallons per hour, that's a good thing. So low on transit time and very low environmental impact. So these are things that started adding up for our team. Reducing the manpower is crucial. And what happens, it's funny, you go out to a Global Hawk launch, and at the first launch, there's 20 people in the room. And everybody's, oh, isn't this great? You hit the launch button, literally it's a click of the mouse, that's how you launch. But you go there at 2 a.m. or 3 a.m. for the midnight shift, there might be 1 or 2 people in the room. So we have some mission scientists in the back. The Navy's version of Global Hawk Trident is flying, they're gonna go down to 1 pilot. And that's what we need to do. I mean, we need to get to a single pilot. There's a lot of autonomy built into this system. We gotta just understand that a little bit more and use it. Here's the great SBIR, and I'm gonna be back up in a couple of minutes to talk about the Aurora group, but I just this was a great SBIR. It's transitioning to phase 3. The reason why the Aurora guys aren't here right now is because they're flying this mission over Alaska. Over California. We're gonna fly this mission later in the month in Colorado, and eventually this plane will be up here in Alaska. And it's been here before to do atmospheric research. So the nice thing about the plane, it burns about 9 gallons per hour. These missions we used to fly with the P3, all right, burns 750 gallons per hour, or King Air, 75 gallons per hour. So we're using 90 to 99% less fuel per mission, and plus it can stay out there a lot longer, a lot more on station. But I'll talk a little bit about more of that in my next brief. So this is another great news story, and I have a video to show you the manned-unmanned teaming and how important that is. But the great thing of this OV1 slide is putting together the end-to-end component. When I'm designing the network, I want real-time imagery to go to your iPhones. I want decision makers to be able to see what we're doing out there, whether it's an oil spill, marine debris, search or rescue. These are all things that we need to put together that network. And also, we try to design in real-time archiving. I think we're all overwhelmed by data. So if you can real-time the data archiving, that'll just be another task off your plate, and you can engineer that in up front. Cool thing here, again, we had Scan Eagles coming from a Licktock Point. The Pumas were out on Healy. We had some unmanned systems in the water. We actually put a raft in the water, a swimmer in the water, a civilian helicopter, and a Coast Guard helicopter went out for the rescue. Okay, and this was all right off of Licktock Point. So we're in international waters, flying beyond the line of sight, multiple platforms in the air, all done very, very safely. And then again, the network, I was watching the whole thing go down on my iPhone at 1 a.m. in DC. This was the spiral developments that took to be successful in the Arctic, okay? And I'm not gonna read them all off again, you're gonna get my slides. But to be successful out here, I mean, including consistent beyond line of sight operations. Now we've gone out to 25 nautical miles down in the South Pole with that, down in the Antarctic with that. We expanded the Puma wind envelope to 35 knots. It was 25 knots. And I just asked the question, where did you get 25 knots from? And I go, oh, that was the requirement. I'm like, nobody tested to higher. So we've tested up to 35 and you can do it. You're wrestling with the plane, and it's better to use the launcher in that case, but you can launch at 35 knots of wind. The autonomous net capture system, all that testing was done on NOAA boats, and then we transitioned to Coast Guard, now the Navy's using it. So these are all the things, and again, working on the data management component is really important. Here's the testing that we did yesterday, and again, you got a great briefing on the marine mammal component, but here's the atmospheric sensor that I'm talking about. That costs $100, and you could put that into a thumb drive. It has its own energy source, so you just can put that onto a small UAS. We're doing that on several different platforms. In the next couple of weeks, there should be an endurance record set. A small plane's going to stay up for about a week, and 2 of those sensors will be on. I gave to the guys who are doing this. So we're going to have an atmosphere. We're going to have a week's worth of atmospheric sensing data from doing that mission. Again, this was the Scan Eagle mission discussed yesterday. Here's the recovery. This is Barrow. We also put the PEMDAS system on. We talked a little bit about that. That atmospheric sensor, but the good thing about that is it looks like a pitot tube, but it's an ice prediction system. So as a P3 guy, I fly into icing, all of a sudden I get an icing light. If you fly into icing with a small UAS, it's too long, it's too late. You're gonna go in the water, all right? So it's better to be able to predict when you're gonna go in icing, so you can make the U-turn before you actually go into icing. That system's gonna be put on Gray Eagles. We're trying to get on the Global Hawk, and it's giving scientific atmospheric data, so again, doing a NOAA mission, but it's also a safety case because it's helping pilots stay out of icing. They've been working on having a turbulence detector and also lightning detector on that too. And that's the fair weather, by the way, on the bottom. And we did a successful handoff on that Scan Eagle. So there was a control station there. We didn't have a recovery system there, but we did a handoff. So this is what we're talking about with the rapid response. We've been looking at this quite a bit. And this is the evolution of the requirement. At T-0, when you have an emergency, what do you need as a leader? You just want full motion video and imagery. You just need something for situational awareness. Over time, the requirement will evolve. And so this one here is what Eyal's going to be talking about shortly. This is a Real Forecasting Center mission that we did this spring out of Circle, Alaska. But this was an actual oil spill last year in Santa Barbara. And we had mosaic imagery within a day. Now this is more complicated, but this is a graphic of the Global Hawk flying over a hurricane. Believe it or not, we have pretty sophisticated sensors on board where we've gotten to being able to pass that data with good visualization, near real time. So all these things, in the old days, this timeline to do ortho mosaicing would take days. We're getting that down to hours. In certain planes, you get it real time in your cockpit. It's expensive, but it's already being done. So our goal is to move the timeline this way with more and more sophisticated data sets, and that's all work. Here's our Arctic rapid response. And again, we've done a lot of different missions up there. Oil spill drills, marine debris. Here's our search and rescue mission. All that data has had end-to-end going into our environmental response management application. So we have a common operating picture. We feed our data from all these different systems into that so we can share it on ship and off ship. So very, very successful. But I remind everybody, every emergency starts local. We were talking about this in Hawaii. When you have your Hawaii team there, they can get airborne within minutes and hours. But if you try to get somebody from California out there, it's going to take a couple of days. So think in that local response mode. And sometimes, again, initially you want imagery, and then you'll step out from there. So easy systems first, and then more complicated or more advanced systems if you need them later. Here's some satellite calibration and validation work we're doing with small UASs. So this is with the GOES-R program. We've integrated some sophisticated sensors on both fixed wing and small UAS, and we're going to do GOES-R CalVal. So the VIIRS, we were talking about VIIRS this morning. Those sensors we have on board, thermal imagery, atmospheric sensor, simple EO/IR on board, but that's going to help us do the final satellite calibration. And this is it, and people keep bringing this up time and time again. The partnerships are important. If your logo's not up there, get it up there. We're always reaching out to work with others. We've been very successful in Alaska and in the Arctic because of our partnerships, and we're planning to have more successes in the future. The Arctic and shipboard operations are very, 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 very challenging. I tell people, hey, when you start on the land in the Arctic, that's hard. The second you go to the boat, it's about 10 to 100 times harder. So a big leap. When we're doing work, decreased footprint's important, right? Because it's hard to move this stuff around. Robin mentioned it yesterday, getting all our launch and recovery gear for the Scan Eagle out to Barrow was complicated. Now that we have a place in a Licktock Point that can support this and is just a drive away with the Scan Eagles that the University of Alaska has, that makes it more enticing to us. A lot less logistics. We don't have to get a C-130 to bring all our gear to remote sites. Making sure that we continue to evolve the platforms, the sensors, and using Moore's Law, things are getting cheaper, funnier, and faster as we go. So we've seen a lot of successes there. Partnerships are crucial, especially up here where it's very dangerous to operate. So we want to save our platforms, our sensors, but most important, our people. And then I'm going to talk a little bit more about science and technology to research and development, test and operations, or test and evaluation operations. So there's a flow there, and there's a lot of mechanisms to go through that whole process. And I'll talk a little bit about that later. And that's my last slide. If you can just show that video. Great. So what you're going to see is a video. This is part of that search and rescue exercise. Again, Puma, Scan Eagle, a civilian helicopter, and a Coast Guard helicopter. That's the back of the Healy. You're looking at Puma IR at about 1,000 feet right now. We're in an orbit above two-man aircraft. So there's the civilian one, and there's the Coast Guard one. We've already found the raft in the water. Now we're guiding these guys over to do the pickup. And they actually put swimmers in the water here, so that was pretty neat. You see the raft right there? Stuck out pretty good. So on the first day, we had the Scan Eagle flying with us out there. So we had Scan Eagle, Puma, and the 2 helicopters. Scan Eagle didn't make the second event. There was a lot of tough weather at Licktock Point those couple of days. So again, when you're flying from the beach, you have to worry about your takeoff weather and your recovery weather and your on-station weather. With the Puma was already on station, so we only had to worry about the on-station weather. So those guys were flying when the beach was still in. So that's it's a good shot of the manned, unmanned teaming and how you can, if you have a good strategy, you can put this together and make it work very safely, very safely. And that's all I got. Robert, sorry for going over. So one of my good friends and colleagues, Dr. Robert Moorhead from Mississippi State's up next, and he's going to be talking a little bit about the research we've done for the National Weather Service's River Forecasting Center.
So it's always tough to follow JC. I don't have the backing of the federal government. All I got is a little university down in South Mississippi. So anyway, what I want to talk about is more science. So this is not about plans. This is about what we did, how we did it, why we did it, and how it affects real people in real places. So I'm going to talk about several things. The first thing is mapping waterways and habitat. I'm going to talk about floods. Second thing is environmental studies. We're going to talk about forest fires and the extent. We're going to talk about sea level rise and stuff like that. So that's what I want to talk about. The work, as JC's already indicated, all of this is joint. JC's talked about most of the partners. The Northern Gulf Institute that I'm the director of involves 6 universities now. So it's not just Mississippi State, but we are the lead. A lot of this work was done with the Lower Mississippi River Forecast Center. So one of the 14, I never can remember numbers, 14 to 19 to 16 RFCs in the National Weather Service, and then with the Grand Bay National Estuarine Research Reserve. So the first thing I want to talk about is a flooding project, Shout for Rivers. So we tried to build off of the larger Shout project that NOAA was doing. And the goal here was to map waterways, sediment transport, and the vegetation around this marsh area. The goal ultimately was to have an updated stream network and improve flood forecast. So why we were doing this? Let me talk about where, and then I can explain why. So this little bright green little square there, I tried to give a larger context, hopefully you can get some idea, but it's between New Orleans, Louisiana, and Stennis Space Center, Mississippi. And I hope many people in the room at least know where New Orleans is. So it's northeast of New Orleans. it looks like this lower area down here. It's a marshland, river marshland. So why this area? Well, back in 2005, we had this little thing called Hurricane Katrina. Came in and it just swamped this area, just totally changed, knocked down trees, lots of stuff changed. Well, so that happened. Drove a lot of people out of New Orleans, and they moved out of New Orleans to the northeast and built on the edge of this wetlands research, or wetlands management area, national wildlife refuge, lots of birds, pretty trees. Nobody would ever build there, right? So your backyard, you've got this just pristine, birds coming in, sun coming up area. It's Green Acres 2010, okay? So everything's great. Well, along came Hurricane Isaac in about 2012, and the National Weather Service, the Lower Mississippi River Forecast Center, was very challenged to predict how high the floods would go because of all the change in the environment from Katrina 7 years before. Well, when they built these houses, they built them on stilts up to 20 foot. So they were preparing for a 20-foot flood. Couldn't determine really whether it was going to be 19 and a half or 22. So question was, if it's going to be below 20 foot, we're going to stay. If it's above 20 foot, we better evacuate. Turns out it was a lot of people evacuated. The flood was about 19 and a half. That was the crest. Not much structural damage, but a lot of looting. So this is part of why NOAA has this weather-ready nation focus on loss of life and property. What we want to try to do is to build better flood models and predictions of how water is going to move. A lot of these hydrologic models are built on static digital elevation models. Static environment, the water changes, which is not realistic. And Isle and others will get into that later today. So how do we go about mapping this? We got a 20 square mile area that we're going to map with 2-inch resolution, which is a little bit overkill, but it got the job done. And as JC often talks about multi-mission, I'm going to talk about this data set used in a lot of different ways. So on the top here, we're actually launching an Altadian Nova out of a 14-foot, 20-foot boat just along the river. And in the bottom center, you're going to see it come in for a landing. Now, this is a little bit harder to see. It's going to come in from your right and land almost in the center of the picture, but it's a little hard to see. So let's see if I can make it work. Yeah. So, yeah, can you see it? There, it hits the water. So this thing was in the F6500. The earlier model is water repellent. The new one is more or less waterproof. So what we would do is we'd launch this 15, it's a Puma size bird. So 9-foot wingspan, about 15-pound bird. Launch it. Originally, in the first flights, it was flying about an hour, and as technology got better, we could go about 2 hours, cover about 2 square miles in the end, 1 square mile in the beginning. We did 9 missions over about a 2-year period, so that we could get the sediment transport, the seasonal vegetation, and where the water was at different levels, different times. So what we generated here, with about 15 to 16 flights, is a mosaic like this. A couple of explanations. The reason it's kind of pinkish or purplish is we used a color infrared camera so that we were able to differentiate healthy vegetation from unhealthy and water from land much easier. Why the different colors or splotches? Well, we chose to mosaic this per mission. So every time we flew for an hour or 2 hours, we collected approximately 1,000 images. We went back and mosaicked those together and created one mosaic. And so then we just laid them all down together. So you're getting different sun angles. We're not always flying at solar noon, and you're getting potentially different weather, so different light. So that's why, this is a trade-off between what is the data really like, what is the image like, versus creating a pretty picture. And this is one of the things that we have to deal with in creating maps. Okay, so if I zoom in to about 1.5 kilometer square area here, the imagery that we took over 3 different times, so December, August, and next December. What we've now done is we've normalized the atmospheric and the radiation so that it's capturing the same environment under the same lighting conditions. All right, and you can probably start seeing some of the differences here, which is what we were trying to tease out. If we map to just land and water, and if it's not obvious, land's green, water's blue, you can begin to see a little bit more of the difference. We can do better classification here. This was just kind of a simple first cut, trying to explain how things changed over seasons. If we zoom into this 50,000 square meter area, so going from 1.5 million to 50,000, and we zoom in and look at that one area, these hair follicle-like images. That's what one of my colleagues said. They look like little hair follicles. You can see the change in the area, especially right through here. Right? There's less water in August. That's what you would expect in a semi-tropical, subtropical area. And at the first mapping here, this looks like, land has come in there and trees have grown up, right? Well, some of this is actually floating vegetation. Another thing we have to tease out of this is, what is the tidal level? Are we getting a different tide? Is this area very tidally driven? So those are some of the things that the PhD students and other researchers are actually working on at this point. This also works really well for a lot of marsh restoration work that's going on. We can monitor how those marshes are being recreated, or vegetation coming in. Is there areas for the fisheries to move through to keep their health? So let me move on to the Grand Bay Near. So this was, the first part there was in southwest Mississippi, over in Louisiana. Admittedly, it was a little bit more in Louisiana. This is in southeast Mississippi, so near Mobile, Alabama. This is one of the National Estuarine Research Programs, Grand Bay. The red outline there is the extent of the near. So we did this work, I guess I don't have the dates, yeah, I do have the dates up here on some of this. We've reflown most of this area, and as JC insinuated, some of the funding that the UAS Program Office put out internally to NOAA, they're going to do yet a third study. So because we did this work for 1 year and then another year, and then they funded this other work, next year there's going to be some more studies on this. So I'll try to insinuate, or at least hint at what I think I know about what's going on here. There were 4 studies we did. So given the success we had, Grand Bay called us, NEAR called us, whatever, and said, hey, maybe you could help us with some of our research, some of our environmental studies. Maybe the UAS would help us do things better, cheaper, faster, all the nice words JC likes to use, efficient, economy, etc. Okay? So the first one we did was what they call their Centennial sites, and they're all in this area, and I want to go into that in a lot more detail here in just a second. Doing that work, which I'm going to talk about second, is some disaster response work. I'll go into detail. That was all the way over here, and this is actually an oil refinery. I won't say the company name. I'll talk about what's up here in just a second. And then with that result, they called us back and said, hey, can you come help us with some wildfire studies? Or actually, I should call the first one a wildfire, the second one a human-induced fire. The thing to notice here, I really want to point out is, it's like your toolbox. I mean, most of you guys that have on boots and nice jackets and do real work, you don't just have one screwdriver or one hammer. So I'm going to get back to that, but I want to go on and say it. There's three different UASs in here. There's various cameras. We flew at different altitudes for these missions, and we got different resolutions. Okay, so these aren't a one-off solution. It takes a tool shed of tools to do this work. All right, let me jump into this. So the Centennial sites, what they're trying to do here is determine sea level rise, and they've got 4 areas here. They're marked over here with these yellow polygons and broken out here. And they've gone out and put sediment, surface elevation tables. These little red triangles indicate where they've got tables out there where they've gone in an RTK and measured very precisely what the height of the land is. The way they traditionally have done this is they then go back with this long pole and they measure exactly what the height is at these places. And they use LiDARs and lasers and all kinds of stuff. They drag a bunch of heavy equipment out there. So the question was, can we come in with a UAS and do this a whole lot better? Along the way to doing this, I want to talk first about this area, which is the largest, the salt pan, Upper Juncus. And then I'm going to focus really down here on the Spartina area. These areas are not very large. I admit that right up front. You can see up here, this one's probably about 50 acres. Well, this is more like 50 acres, just a little bit smaller than that. The 2 species of interest here, of great interest, are the Juncus, which is black needle rush, taller, right along the water, and this Spartina, which is this lighter green gas. I'll explain why here. It turns out that black rush likes to have its feet at high tide. Spartina likes to have its feet at low tide. So, determining the interface between those two determines where sea level is. To change that interface determines sea level rise or subsidence. Pretty smart, those wetlands biologists. So, the first thing is I want to kind of give you an idea of the resolution of these UAS and what you can do. Most of you in here know this, but I just want to make sure. This was about a 50, as I said earlier, a 50 acre area. Zooming in on this area over here, and then coming down to this one, we now are getting 2-inch resolution from an $8,000 UAS in about 40 minutes, and these are 8-inch boardwalks. This is how they got out, or how they get out to the surface elevation tables to actually measure the change in the height. Okay, so in 40 minutes, we're able to fly this $8,000 bird and get 2-inch resolution over this 50-acre area. All right, so let me move to the Spartina area, that part to the most south, and this is the reason. This is a WorldView 3 image that was taken 11 days before we went in and flew the UAS. So this is some of the best satellite imagery you can get, 33 to 44 centimeter resolution. Pretty good picture, something you might actually see here in Alaska. This is the UAS image, at least part of it. We only flew part of it. So the color's a little bit different, but they cover closely, they're overlaid on each other. Let's see if I can go back and forth a couple of times to convince you. Well, there's an absence there. There's a couple of things. Most people would realize one of the issues here. This is due to the fact that it's like putting cloud puzzle pieces in a jigsaw puzzle. They're all blue. You don't know where they go, right? So the mosaicing software can't really determine that, but that's not a problem here. For the scientists, what they're interested in is the edges here. So we're in good shape. Doing a species classification of the WorldView 3 image, the satellite imagery, mapped it to 5 different classes. 4 of our greatest interest here. Flooded marsh is this dark green, water is this blue or purple, and then the Spartina is this bright green, and the Juncus is the purple, okay? And then there's black is this other marsh grass that's in here. That's the satellite imagery. That's the UAS image. I'll go back and forth a couple of times. You can see they're pretty well correlated, right? So what's the big advantage of the UAS? Okay. This is a zoom in of that satellite imagery. Those sediment elevation tables are 1 meter square boxes. They're shown there in those little red boxes. That's 40 inches by 40 inches. Notice how little variation you get in those places that they traditionally have sampled. Only about 2 of them is there actually any other color than 1, right? There's only about 1 or 2 that actually have 2 colors in them. This is the UAS image. So with this image, you're getting 2-inch resolution in that 40-inch box. So you can see real quickly, I'm not zoomed in as far, you can't really see the pixelization yet because you're getting, 400 samples in that 40-inch box. So rather than sampling with the satellite imagery as an alternative here, instead of just getting what you got, you get a whole lot more resolution here. You can determine the change in the species composition, each one of those levels, which tells you whether it's above sea level or below sea level. It's much faster, it's much cleaner. You can see the 8-inch wide boardwalk out through here in this image. So now instead of having to drag all that heavy equipment out there to measure the elevation changes, go out there and sample the grasses instead of stomping all over them, the things they're trying to protect, you can fly this small UAS for 40 minutes and get this data and more. All right, let me go on to the next one. This is pretty straightforward. Simulated chemical spill, there's a phosphorus plant, chemical fertilizer plant that's just to the west of Grand Bay. They put the waste in a diked area, so when they get the heavy rains, sometimes there's leaks or bleaching, kills fish, kills grass, etc. So they haven't had a major one except for a hurricane situation, and believe me, in the hurricane situation, other things were of greater interest. But they wanted to try to understand how they needed to monitor that and how to study and how to kind of deal with potential disaster. So all of us got together. We, Mississippi State Engineering School, did not plan the location and how this boat was tied up. This is not the way you want to release a floor scene. You would much rather it come off the backside, not underneath the boat, but that's what happened. So all we did was take the imagery, and because, as has been pointed out in several of these cases, just the video documentation, they were able to go back and look at the videos and some of the stills we were able to take and look to see how things were going, how they were evolving, where they were going, and what the situation was at a certain amount of time. Marsh fire. So the first one we got was in July, first call we got was in July 2015. They had a lightning strike, burned about 1,700 acres. So they were very interested in the extent of the damage, the amount of damage, and then over time, the regrowth. I'm not a wildlife forestry guy, so I don't understand all of the stuff, but hopefully some other people do. We've gone back and reflown it. Grand Bay is now looking at that, trying to understand how the evolution goes. We used an Altavian Nova. It took us 2 flights, covered all 1,700 acres, got them 2-inch resolution. Only took a couple of people. Let's see, how much time do I got? I made the last few here because I didn't know how long JC and Justine, the rock stars, were going to take. So I kind of threw a couple, or made some stuff at the end so I can talk about it to the extent I got time. I got about 3 or 4 minutes. So, as JC talked about use of data. We took that data in the lower Pearl area near the lower Mississippi River Forecast Center, looking to develop data that would allow them to develop time-varying flood models, so they could get a better flood model. In doing so, the guy that was driving the boat has actually got a master's in wetland biology, is an invasive species expert. He looked at the imagery and he says, man, you can see the Phragmites, which is an invasive species in here. And he said, he came back and asked one of my image processing guys that does classification. He said, hey, Satish, can you write an automatic algorithm? You know, this is what Robin needs, by the way. An automatic algorithm to delineate these Phragmites. So we've done research, got 2 journal papers, one published, one submitted. So what's over here is the guys walking around with a GPS around the Phragmites and indicating this is how they classically do it, where there's an invasive species that the Department of Marine Resources needs to go in there and eradicate. And over here, the red is where the classification algorithm actually determined there was invasive species. So you can see the red inside the yellow, and there's a 90-something% match, which was pretty darn good. And if you care to talk about it, I actually co-author on the paper, so I'll understand more about all the pros and cons and how it worked and what didn't work and stuff like that, but we'll do that offline. So that's worked fairly well. The interesting part of this is the way we did this, and this is a little bit of a story. They actually did part of this, ran the algorithm to see if it was close, and then they went back to get more. And then they went back to fly it with, this was with an RGB camera, as you can see, went back and flew it with a MicaSense Red Edge, a multispectral camera, ran the algorithm and got nothing. I mean, almost nothing. And Satish said, great, I don't know what's going on. And they went back and looked at the imagery, and this is in Louisiana. The Louisiana Marine Resources had gone in and burned exactly the area that we had indicated there was Phragmites. So we got complete independent validation of both the yellow, the hand walk around, and the red, the computer classification of what was there. So that's hard to put in paper, but that was really it. Done good. Okay. Deer Island, from all that work, we've flown barrier islands. I talked about Marsh Reconstruction. It turned out the Corps of Engineers rebuilt this. This is all sand, and they're looking to see how much is going off. There's some dredge material in the front where they're rebuilding. They're interested in the bird population, ospreys down here. So we've gotten RGB and CR image on that. So there's just more and more coastal work going on. So I could talk about this, but I don't have time. These are a lot of the other areas we're working in. This is the one I want to talk about. So besides Jay, I'm not sure all's FAA in here. This is not a condemnation. This is just the challenge they've got. So when we asked permission to fly in the Pearl River watershed, we asked to go up to 1,000 feet. And we were told, well, there's rotor traffic coming from north of there out to the oil rigs. We really would rather you stay 800 below, so we only will give you up to 800 feet. Because we don't want you to get up in the rotorcopter traffic, okay? So multiple times we've been out there operating, and we've yet to be overflown. Multiple times we've been underflown. And this is evidence of one. This is a Huey Cobra that underflew us, and they came back, as most of them do, to look. Well, what's going on? So I know we're supposed to get out of their way, but literally this day, because the observer was well within visual sight, started down. Turns out that guy was underneath him. If we had come down as quick as we could have, we probably would have had an issue. So how close are we? You can count the number of pilots in that glass cockpit. You can see how good that camera is by the fact that blade is that frozen, okay? They were that close. So JC showed you Puma overflying helicopters a minute ago. You got to work together. In this case, these guys were probably coming out of the Bell Chase in New Orleans, flying along the coast, just, dilly-dallying through, didn't pay a darn bit of attention to our NOTAM, didn't have their radios on, didn't make a difference, okay? Yes, we report it. So, in summary, as I said earlier, I really think it takes a shed of tools. Not a toolbox, these things are too big. You need a garage. Okay, we work with smalls mostly, we're moving up to larger stuff. Multiple UAVs, fixed wings, rotors, multiple payloads. It's the same software. It's Esri, it's MATLAB, etc., that you can process the imagery with to find birds, to find fish, etc. That's what you've been doing with satellite imagery, manned imagery for a long time. JC and I were asked to help somebody from Wells near up in Maine, in Lindsay Spurrier from Grand Bay, actually write a report that takes a lot of this knowledge and helps those people that might be deploying these small UASs to understand cost, choices, rules, etc. So that's available, I believe, from NOAA at this point. I think they finally finalized that. And with that, that's a list of, my co-authors, and any questions? Kathy may want us to take it to break.
Thank you. So we are right on break, so we're going to be back here at 10:30 because